can start a little bit and then we will see. So can you see the white page? Can all of you see the white page? Yes or no?
Yes, sir.
Okay, you can see. Okay. So today there is a last lecture, and today we'll be doing second order linear hyperbolic equation. So we have done elliptic equation, right? Elliptic equation. The examples are, what are the examples of elliptic equation? The Laplacian of u equal to 0 or f. We have done this, right? Then we done parabolic equation, which is known as the heat equation, right? That is ut minus Laplacian of u equal to 0 or f. This type of thing we have done, right? And then we will be doing today is the hyperbolic equation. These are the model problem, that Laplacian u equal to 0, harmonic function Laplace equation belongs to the elliptic equation. Then we done parabolic, and then we will be doing hyperbolic equation. Okay, first of all, I should define what do you mean by a hyperbolic equation. Okay, so let us start with the definition. The second order PDE, you know what is the second order PDE, or the n a aij u by del xj plus I equal to 1 to n vix cx of u equal to n, with the standing assumption is that the matrix aij is symmetric. Aji is called hyperbolic if all the eigenvalues of A of A matrix Aij are non-zero. And out of that the coefficient, the dimension is n. So out of that n minus 1 of them has the same sign, and remaining one has the opposite sign. You understand? A second order. So this is a standard. Always we in elliptic also we write down this equation, and we call this equation is called hyperbolic if all the eigenvalues of the matrix Aij are non-zero. That's clear. And out of that there should be, it's a symmetric, right? Symmetric, so eigenvalues are real, and out of that n minus 1 of them has the same sign, and remaining one has an opposite sign. And do you remember what happened for the parabolic equation? Yes, we call this type of second order elliptic equation a parabolic. This equation is called parabolic if the matrix Aij, this is the symmetric, and what is that? Anyone? At least one of them has a, you remember, 0, right? And others have the same sign. Elliptic, you know that all the eigenvalues will have a same sign, right? And no zero eigenvalues are there. Okay, so these are the three classification of PDE. Okay, second order partial differential equation. One is called elliptic, parabolic, and another is called hyperbolic equations. Okay, so you know definition of elliptic. So examples of elliptics are the Laplacian. You know parabolic things. Parabolic is the heat equation, and last one is the hyperbolic one. and we should say that what is the example? Can anyone tell me what is the example? Example is the famous wave equation. This is called wave equation. That is, what is that? UTT minus Laplacian of u is equal to 0. X is in Rn and t positive. So domain, your domain, this domain omega is nothing but Rn, sorry, Rn cross infinity. So you just see. So what would be the? Can you tell me what is the matrix? This will be anyone? This will be 1 or all are minus 1. 0, 0. This is the energy matrix. So one eigenvalue, all of them have the same sign, and one eigenvalue has no. All are non-zero eigenvalues, and all of sorry, that will be minus, and all are plus. All are plus eigenvalues, and one are x, and one only this t as a minus 1. So all the eigenvalues are non-zero, and n minus 1 has the same sign, and the other is the opposite sign. Okay, so this is the famous wave equation. Okay, so Laplacian is Laplacian u equal to 0. We have studied this. Then it is ut minus Laplacian of u 0 equal to 0. This is harmonic functions. Harmonic function. It's called Laplace equation. It's called heat equation. Rest another is the wave equation. Okay, so this is a model example. Okay, so now we will be doing little bit of wave equation. Okay, just we will do at least the one dimension case. Okay, so just write down, write down the above wave equation in dimension 1. So this is in Rn cross 0 infinity. Let us see how it looks in dimension 1. Okay, is n equal to 1. This is utt minus uxx equal to 0, and u of x0 is gx, and ut, it's the conditions given, is hx. The domain is r t positive. So this is r cross 0 infinity. This is r cross the boundary condition or the initial. So this is the model problem of wave. So see uxx and utt. So this is a model problem for wave equation in dimension n equal to 1. So when we are in the higher dimension, this uxx will be transformed to Laplacian of u. You understand? This is the called the famous wave equation. Let us try to solve this one dimension case. So any idea how we can solve this one dimension case? Any idea? Anyone? So the equation is now our utt minus uxx equal to 0. So your domain is this. So any idea how we can do that? So is this familiar with something? Huh? Is it familiar with something? Do you remember anything? Have you seen this type of equation in this type of domain? Huh? Manish, Shammi, Kritika, Ankit, Yash, Vivekanand, and Govind. You remember anything? Of course, it's not exactly like that, but something like that. Forgot the characteristic equation. Characteristics, chapter 1. We solved, right? First order characteristic. like this type of, yes or no?
Yeah, yes, sir.
So it is very similar, but there are it's
Higher
not.
level.
So so we want to solve this problem. So now can we rewrite something so that we can use this first order case? The idea is that. Any idea? Huh? You can write this equation. So this is the equation. U of x0 is gx and ut of x0. We will see what are the conditions. Okay. So the above equation can be rewritten as this. Yes or no? This utt minus ux I am writing in this way. Yes or no? Can we write this? Can I write this? Yes or no? To bolo.
Yes, sir.
Okay. So now can we, any idea how we can solve this? Something
Second, transform our variables x and t.
exactly. Write down let vxt. You just define vxt to be first one del u by del t minus del u by del x. Just write let. So first one. Then what equation v satisfies? Anyone? Sorry. What equation we satisfy? Huh?
Vt plus Vx equal to 0.
Very good. Then Vt plus Vx equal to 0. Did this something reminds you? Huh? And of course, what is Vx0? Ut at x0 minus ux at x0. You know ut at x0 is given hx. Sorry. That is your hx and ux at, you just check ux is g prime of x minus g prime. Now write down this new function rx. So now what we satisfy is the following: the equation vt plus vx equal to 0 and vx at 0 is some function rx. I know what is explicitly rx is. Just write down rx, and your domain is r cross 0 infinity. This is r cross 0. Can you solve this equation? Who will tell me? Manish, tell me. What's the solution? This is the first equation we did in our course. What is the solution? And how we solve this? Huh? Manish? Shammi?
Just will like it will be like vx minus t, and then from there we get like v.
With use method of first equation we did this. Method of characteristic. These imply, if you remember the first class, second class I think, p of xt is the solution is given by r of x minus t. Remember g of x minus y is the solution. You remember in there we have ux plus uy equal to 0 and ux at 0 is gx. The solution is u is the solution, g of x minus y is the solution. Okay, so the solution is this. And of course, we know what is Rx minus t. Rx minus t can be written in terms of this is h of x minus t and g prime of x minus t. Okay, now what we will do? Now, now substituting back. So we have defined vxt is them. Now we know explicitly what is vxt, r of x minus t. Now what I will do? Huh? Now what I will do?
And again, apply method of characteristic.
Yes. Now, sorry, maybe I have done mistakes. Some mistake I have done. No, that's okay. Now we know that this is so this is okay. So this I have solved. This is vxt. Okay. So now you substituting back. Substituting back. We get what is ut minus ux is equal to vxt. Well, this is our assumption. Vxt is nothing but del u by del t minus ux. You will see. Okay. Okay. So now the equation is, now we know that this is r of x minus t. So the equation transformed to ut minus ux is equal to some function r of x minus t, and u of x at 0, we know that it's gx. Who will tell me now how to solve this? How to solve this? Again use method of, we have done this also, method of characteristic. If you write, if you see our solution, it will be u of xt is g of x plus t plus half. This is because of this non-homogeneous term. This will be x minus t, x plus t, r of s. You can see our, you can check your notes. And now you again use the characteristic method of characteristic. Okay. Now what is RS? So uxt is now our uxt is g of x plus t plus half x minus t x plus t. What is RS? R we know, explicitly we know R. What is R? This is your R. R is hx minus g prime x. Just a minute. This is h of s minus g prime of s. This is R. I just substituting R into ds. This I can write as x plus t plus half x minus t x plus t take minus g prime of s. Okay, plus half x minus t hs ds. Okay, is that okay? Now what I can write this? Anyone? G of x plus t. What I can write this? Huh?
g of x plus t minus g of x minus t gx.
Half g of x plus t plus half g of x minus t plus this quantity remains plus half x minus t x plus t hs ds. This remains. Okay, this remains. So this is equal to, you can club it this, g of x plus t plus g of x minus t plus half x minus t, x plus t, h of s. Okay, so you can write explicitly the solution u of xt as written as g of not this one. This is solution x plus t plus g of x minus t by 2 plus half, because g is given condition, right? G is known. X minus t, x plus t, hs. So this is the solution. Okay, and this famous formula is called the D'Alembert's is the D'Alembert's formula. Okay, so once the one-dimensional wave equation is given with a proper initial condition, that means utt minus uxx equal to 0. U at x comma 0 is given to be g of x, and u at that point of x, u derivative with respect to t variable, it is given hx. Then your solution is given by this way. So everything is known. See, you write down the solution in terms of the initial condition, right? Is that okay? Okay. Now conversely also this is true. Conversely, this is very interesting. Conversely, if G is C2 of R and H is C1 of R, then you defined by the formula solves the this Cauchy problem. That you are clear, right? Just you just define u of xt by this. You write down uxt. This is if u is a solution, then u is of this form. Now the converse part, you know what I am mean to say. Suppose g and h are given, you write down this. Then if you derivative this u prime, it will satisfy all the condition of the Cauchy problem. Okay. Okay. So interesting remarks. The above formula, the D'Alembert's formula, the above formula is of the form f of xt plus g of x, right? Is that clear? See, it is of the function g of x plus t plus, but if you write down in a proper way, this is for some capital F and small g, capital G, for some capital F and small g. Right? Yes. Is that clear why I'm saying? Because this is also in terms of x plus t and x minus t, and this. So uxt is nothing but uxt is can be written as the above formula can be written in terms of f of x plus t and g of x minus t, right? For some f and g. Conversely, if you just see, conversely, you let u of xt is equal to some f of x plus t plus g of x minus t. Then clearly, if you just utt, you make utt minus uxx, then this is equal to 0. So the D'Alembert's formula is nothing but it is giving you the solution in terms of the translate of x plus t and some function of x plus t and some function of x minus t. Okay, so you can completely solve the Cauchy problem using D'Alembert's formula. If you want to study this Cauchy problem, then you can immediately solve this using dual inverse equation. Is that clear? Chitram, Govind, Vivekanand, Yash, Ankit, Kritika, Shammi, and
Yes,
Mani.
sir.
Clear? It's very simple, right? Just using a method of characteristics. Okay. So I think I should not go far. So you can also now the Cauchy problem in higher dimension. Cauchy problem. In higher dimension. Okay, what is that? UTT minus Laplacian u equal to 0 when xt is given in Rn cross 0 infinity when x is in Rn and ut at x0 when x is in Rn. Okay, so this is a Cauchy problem in higher dimension. Okay, so so okay, so the main now the aim is to solve the above solve the problem above problem. Okay, because now instead of uxx you have the higher order, that is Laplacian of u, because now we are working in a higher dimension case. Okay, and the wave equation means utt minus Laplacian of u equal to 0 and u equal. So can we have a closed form solution? Can we have a closed okay, can we have a closed form solutions? Okay, like the case like the case as in okay, so the idea is I will not prove that. The idea is we have to do something to prove solve this type of OD. We have to introduce a notion called spherical means. Spherical means. Okay, I will not do that. Set spherical means. Okay, so what you have to do, define what is a spherical mean. Define for x in Rn, t positive and r positive. You define u of x t r as del bxr u y t or fixed t, it d sigma y for fixed t. Okay, so that is why called spherical means. That means I am so you know this sign. What is this? You know what is this? This is nothing but of course you know this sign. This sign is nothing but 1 by you Laplace equation like del bxr del bxr uyt. This is called average. You know what this cross means. This same thing. 1 by the measure integral over this. Okay. So these function will play very important. These are the spherical means. You know why I said that. This is something called the mean of the something averaging out the integral averaging out the integral by the total mass, right? So this is some kind of averaging out. So with this uxtr, we will show that. So first we have to, this is this function defined for r positive, t positive and x, right? Now we have to define this function when r is negative also. How to do that? Okay. So for that we have to extend uxtr gxr and h of xr. Okay, I sorry. Forgot to define g and h. G of xr is nothing but same thing. Del b xr gy d sigma y. Okay, and hxr is del b xr hy. Okay, now I have to extend for r negative these functions. Okay, so extend u of x tr, g of xr, and h of xr for r negative. For r negative. Okay, how to define? You define uxt0 because r is first case r equal to 0. You write down uxt. Okay, and rest uxtr is the even reflection. That means this is uxt minus r negative. For r negative, you know the how uxt defined for r positive, right? Now when you are r negative, just make minus r. Then minus r is a positive. Then you can define it this way, right? Okay. Similarly, you do this for g of x0 as g of x and g of xr as g of even. You extend the function evenly, okay? And h of x0 as h of x and h of xr is hx of minus r. So the extension is done, right? Now you define a function b of rt of x dr for fixed x. Fixed your x and define this function. So of course this is dependent on x like that. You fixed your x, okay? Then you can check that these v satisfies this equation. This is not a derivative of x. Just don't mix with that. That's better. Vtt is equal to vrr plus n minus 1 by rvr. Vr0 is nothing but gxr and Vt at R0 is h of xr. Now you have to use this to solve your, so this is the wave equation, right? Utt minus Laplacian of in R, right? So, but now you have to solve it for something is there. I'm not going in detail. Something, but the idea is these functions play a very important role. The spherical means will play a very important role in solving this equation. Okay, higher order problem. Okay, what is the spherical means doing? Can you see that? So you are just averaging it, means the function now depends on you are making a new parameter, introducing a new parameter r, which is just like a one dimension case, right? Because this x, because we want to solve something for x, Laplacian x is in Rn. So you are introducing some r parameter, so that you make a r means r varies from minus in r belongs to capital R, and use some function v of r for fixed x v of r, right? So this is nothing but a one dimension. You reduce the problem to a one dimensional case, right? And you have to use some kind of again real D'Alembert type formula or something, because you very well know how to deal with the one dimension case, right? Because v is a function of r, right? So v satisfies this problem, right? So this is almost, it solves, or not almost, in a radial coordinate it solves the wave equation, right? So that's all. I think I will stop here. That's all. So I'm not going in details the wave equation. So at least you should understand what happened in one dimension case, which is the famous D'Alembert's formula. This is very useful in your future purposes. If you are giving some competitive exam or something, so someone asks you how to solve this type of wave equation, the equation is solved using this D'Alembert's. You know how to solve this. This D'Alembert's equation. Okay, is that okay? Clear?
And sir, for non-homogeneous,
There are a lot of things. So if this a how to,
one-dimensional.
again the idea is you have to averaging out, yes, and solve this type of equation. I'm not going into that. There are many cases. So there will be even so dimension will play a very important role. Odd even dimension. So I'm not going into that. If it's an odd dimension, these things are more or less you can write down something. The solution looks different, and in even dimension, the solution looks different. Okay, so there is also an odd even dimension coming to play when you are doing for Rn when I am solving for Rn for n greater than equal to 2. Sorry. So then dimension of even and odd also come into play, and this for even the closed solution is different, closed form solution, and the event case also the closed solution is different. Okay, so so there are many things, and of course, as you mentioned, what happened if instead of 0, if there is some f, okay, non-homogeneous term. So instead of this 0, you use some f. Then how to do that? Okay. So I'm not going into that. So because it's enough for you, but of course you should understand ultra numbers. Okay. So this is very important. Okay. How to solve using D'Alembert's equation. This can be useful in your competitive exam also. Okay. Okay. That's all. I think it's enough. So that's all. You have an exam on 22nd, I guess, right? If I'm not wrong, it's on 22nd, right?
Yes, sir.
Yes, sir.
So it's thank you for attending the class and something. So syllabus, so lecture syllabus will be from lecture 1 to lecture 20. I will write down, or tomorrow I will write down the syllabus. Okay, lecture 1 to 21, and of course there will be part from Laplace heat, Laplace plus heat, not heat full, so something, and first part, the first order, and the Cauchy-Kovalevsky. So this two part you can divide it. First is the first order case. Of course, there are some questions from here also, and of course here. So basically Laplace, I think, I don't know whether it will be 50% or 50% weightage, but I will try to have more on this equation, or maybe 60-40 kind of thing. Okay, now I'm not sure. Yeah, so this is nothing known, but yeah, this is the two main part. You can call it like first order and Cauchy-Kovalevsky, and the second part is Laplace and heat equation. Okay, is that okay? So so the syllabus is this, lecture 121. So I'm not considering excluding the last part of the heat equation and today's wave equation. Okay, so I'm excluding wave plus some part of heat, some part. Okay, is that okay? So thank you. So this was the end. This was the last class. Thanks a lot. I hope you have understood something in PDE. Okay, thank you.
Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Thank you.
Thank you, sir.
Thank you.
Hello, sir.